Hey everyone, this is Dr. Walker. This is video 48C on impulse. Let's start this video by talking about non-isolated systems. As you might imagine, a non-isolated system is one in which a net force does act on the system for a certain time interval, compared to the isolated systems which did not have any net forces acting on them. Let's consider Newton's second law. We just learned in a previous video that Newton's second law could be rewritten as the net force equals the time derivative of the momentum. Well, what we can do now is we can rearrange this equation, just move the dt with the force and have the dp by itself. So dp equals the net force times dt. Now we can integrate both sides. When we integrate the left-hand side, we get the change in momentum. When we integrate the right-hand side, we're going to get the integral of this net force dt. The reason we started off by looking at this non-isolated system in which there is a net force acting is because we get this integral. And this integral of the net force dt here is a very important integral that gets its own name. And that name is the impulse. So we just saw that the change in momentum was equal to this impulse. Let's talk about this impulse first. So the impulse is the integral of the net force, dt. Then if we look at a graph of net force on the y-axis and time on the x-axis, then the area under the curve is the integral. Now this graph shows a force that is varying as a function of time. We could get a time average force here, which is a constant force, right? It has this value here, for which the impulse delivered by this force is the same as the impulse delivered by this time varying force. So the area under the curve of the constant force is the same as the area under the curve of the time varying force. And this simplifies our equation a little bit, and it tells us that if we do have this constant force, then we can rewrite the impulse as the product of the net force times delta t. The units for impulse is Newton times seconds. Now it's also equal to kilograms times meters per second because we learned that this impulse was equal to the change in momentum as well when we were looking at Newton's second law. Impulse is a vector, so it does have a direction in the direction of the net force. And I did make a note here that the impulse is equal to the area under a force time curve. So now let's put it all together. We saw from Newton's second law that the change in momentum was equal to this impulse. Before we get to that though, let's do this question first. An object moving to the right experiences the force shown. What will be its direction after the force ends? So that seems a little bit vague here, but let's take a look. We are given a force versus time graph and a force that is applied for 1/2 seconds, and it's a constant force in this case of 2 newtons over this time interval. But even if it wasn't constant, we know that we can find the impulse by taking the area under the curve. So the impulse is equal to 2 times 1/2, which is 1 Newton times second is the unit for impulse. Now, that's the magnitude of the impulse. What about the direction? Well, the direction of the impulse has the same direction as the force. This force is in the x direction and it's a positive direction, which we are going to assume that is a positive direction is to the right. So the object is already moving to the right and it has a positive impulse corresponding to a positive force that is going to deliver an impulse to the right. Then the direction of the object is still going to be to the right. So the purpose of this example was just to get to practice looking at finding the area under the curve to find an impulse and to kind of get a conceptual idea that this impulse can possibly change the direction of an object, but in this case, because it was positive, just like the motion, then the final motion was also positive. Let's put it all together. The impulse momentum theorem. That is what we saw in the previous couple of slides, that an impulse delivered to an object causes its momentum to change. It came from looking at Newton's second law. We often rewrite the impulse momentum theorem as our force times time, and we're assuming that this is a constant force here, or it's the average force, is equal to mvf minus mvi. I like to think about playing tennis. Let's look at Serena Williams here. She is exerting an impulse, delivering an impulse to that ball with her tennis racket. What's happening before the impulse is that the ball is moving to the right. What's happening after the impulse? The ball is going to move to the left. So the force exerted was to the left. And it caused that momentum to change, right? It caused the velocity to change, which means the momentum of the ball changed because of this force that was applied for a certain amount of time. So that's the idea. Impulse changes momentum. Whenever you see this delta t here, you want to think of this delta t as a contact time. It's usually a very short time. It's the time during which the force is acting on your object. We're going to do some examples in the next video, but I just want to look at a few conceptual things before we end here. So we're going to look at two cases. The first case is one where we have a constant force. When we have a constant force, then increasing that contact time is going to increase the momentum. How do we know that from the impulse momentum theorem? Well, let's think about following through in baseball or tennis or golf, anything like that. When you follow through, you increase the contact time. But you haven't suddenly gotten stronger just because you're following through. So we're going to assume that your force is remaining constant. So the left-hand side equals the right-hand side. Then if you increase the contact time, then that means that the momentum must increase as well. Let me just rewrite the constant here because it did not look very good. So I usually put a little line here to show it's constant, and then we can see that as one variable increases, it increases another. If we rewrite change in momentum as mvf minus mvi, then we can see that applying the force doesn't change the initial velocity, right? It only changes the final velocity. So we can see that if the momentum is increasing, that means that the final velocity has increased as well. Let's look at the other case, which is that of a constant impulse. This time, increasing the contact time reduces the force. So that might sound weird because we just talked about how increasing the contact time increases the impulse and the change in momentum. But now it's increasing the force. So the key here is that there's always a variable that is remaining constant. In this case, we're looking at constant impulse. And if you remember that impulse is change in momentum, then that means that this change in momentum is the variable that is remaining constant. Let's look at the example of increasing the collision time using airbags. When you have airbags, it increases the time that it takes to stop, right? But with or without airbags, you're going to have some kind of initial velocity, and then your final velocity is going to equal 0, whether you have airbags or not. So your change in momentum is constant, right? Your impulse is constant, whether or not you have airbags. So that means that if you increase the contact time, then in turn, the force must decrease so that we still have a constant impulse and constant change in momentum. So that's the idea behind airbags, is increasing that time of contact to reduce the force. Another example that I like to show is a car driving into a haystack versus a brick wall. Which one would you rather drive in, right? Would you rather drive really fast into a haystack or into a brick wall? Well, if you drive into a haystack, it's going to take longer to stop. You've increased that contact time. That means you have reduced that force. Versus when you hit a brick wall, your contact time is very short, and that means that your force is very big. Let's look at examples in the next video.